In this section, we're going to take a look at the concept of separable equations. Up until now, we've been looking at definitions and theorems of existence. We've been looking at what solutions entail, what some of their properties are, but we haven't really seen how to solve anything just yet. In this section, we begin by solving our first set of equations here. We're going to look at what are called first-order ordinary differential equations. That is to say, equations that have one derivative as the highest derivative in the equation. In this chapter, we're going to begin with first-order problems, and we're going to look at techniques that apply to those. That is not to say that this is a complete listing of every technique that's possible. However, this is a listing of some of those simpler techniques that will allow us to extend into more complicated ones later on down the line. So here we're going to look at what are called separable equations, and we should define what that means. So a first-order ODE that looks of the form y prime equals f of x comma y. So first order, first derivative is the highest. This is said to be separable if there exist two functions, which we've already used f, so let's use g and h. If there exist two functions g and h, each of which has a single variable. For now, we're looking at functions of just one variable each, even though this is a function of two variables. Each of one variable, such that f of x comma y, this function here, is equal to the product of g of x times h of y. That is to say, it's separable if your function of two variables can actually be written as the product of two functions, each with one variable, one with x and one with y. It can be separated into these two factors, so that the equation can be rewritten as y prime equals g of x times h of y. Okay. Problems that have this property, ODEs that have this property, are called separable differential equations, or more simply separable equations. And for example, something that looks like this. Let's say we had y prime is equal to the sine of x times the cotangent of y. This would be an example of a separable equation, because here y prime is equal to something that can be separated as a function of x times a function of y. Now, sometimes that is already written. Here, you don't need to do anything. It's already written that way. However, sometimes it's not. For example, if I said y prime equals 1 plus y over 1 plus x, you might think, okay, well, now that's a quotient, not a product, so that's different. But of course, you can always write this as 1 over 1 plus x times 1 over y, 1 plus y. And now I have a function of just x times a function of just y. These are all examples of equations that are separable. And of course, you can always use an equation in Leibniz notation. You can say dy dx instead of y prime, and same thing. So if, for example, I had dy dx is equal to, let's say, x sine of y, that would be another example of something separable, x times sine of y. Note that it does have to be a product, or something that can be written as a product. Right? So all of these here are separable. On the other hand, if I had something like y prime equals x plus sine of y instead of times, well, now that's not a product, nor can it be rewritten as a product. This is a sum. Right? Same thing in Leibniz notation. If I said something like dy dx is equal to x plus y instead of x times y, then these would be examples of things that are not separable. Not separable. Okay, so we have an idea of what a separable equation is. So how do you solve it? Well, in this course, you are not generally expected to do things from scratch. That is to say, unlike in a calculus course where you start with things by definition and then build up from there, here the techniques are going to be rather complicated to build, but in the end, they're going to be extremely formulaic, a lot more so than anything you would see in the majority of calculus. Of course, there is some formulaic stuff in the calculus series, especially in Cal 1, but here it's going to be a lot more so. So when I show you how to do these things, I'm going to go ahead and do it, at least as time allows. I'm going to go ahead and develop these problems step by step, and I'm going to do my best to show you when it's accessible to us. Some things are a little bit more difficult than are appropriate for this course, but when it's appropriate, I will build these results step by step. But in the end, I'm going to summarize that step-by-step development as a single formulaic statement. You are welcome to try to understand the step-by-step. In fact, I strongly encourage it, but you will be responsible primarily during assignments and during exams for knowing the final technique. All right, so let me go ahead and go through one, and then this should better illustrate what I mean. So let's say I had a separable equation. Y prime equals g of x times h of y. Okay, that was separable. And here we're going to have a stipulation that this h of y should not be 0, because otherwise the next step is going to be undefined, where h of y is not equal to 0. Okay. Now, we let another function, which we're going to call p of y, we're going to have that be the reciprocal of h of y. So this will just be 1 over h of y like this. All right. If I do that, then my equation, y prime equals g of x times h of y, is the same as saying p of y times y prime equals g of x times h of y times 1 over h of y. All I've done is I took my original equation, multiplied on one side by p of y, multiplied on the other side by 1 over h of y. After all, those are the same, p of y and 1 over h of y. But by writing it this way, these two divide away, and I'm left with just p of y, y prime, equals, this is gone, just g of x. All right, so now, if y equals phi of x, and that's the notation we use for our solutions, if y equals phi of x is a solution, then I should be able to plug it in right here, yeah? Then p of phi of x times phi prime of x should equal to g of x. Yeah, I'm plugging in my phi of x for my y's. If this is a solution, then I should be able to do that. So now everything's a function of x. I can integrate with respect to x. So the integral of p of phi of x, phi prime of x, this right here, integrated with respect to x, would equal to the integral of g of x with respect to x. If these are equal, then their integrals are equal, up to a constant of integration. Thus, the integral of, now remember here, this is p of phi of x, but phi of x means y, yeah? So this is p of y, and then this is the derivative of y. The derivative of the phi is the same as the derivative of y times dx. Well, the derivative of a function times the differential of the variable of that function, that's just the differential of this function. That's a definition from Cal 1, right? If I take y equals f of x, then f prime of x dx, that's just the differential of y. So here that's going to be p of y dy equals the integral of g of x dx. But then that suggests how we want to solve these. What we want to do is we want to take this expression here, the function of y, bring it to the other side, and then integrate with respect to the different variables, with respect to x and y. This development shows us a final result. This final result, however, is formulaic. You say, you keep saying the word formulaic. What do you mean by formulaic? I mean, there's a formula. Well, not quite a formula. More of a technique. So you've seen that so far I've had headers that are definition. Here's the definition of something. Example, here's an example of something. For the first time, but certainly not for the last, it's going to be a very common header for things. After I develop how a process is supposed to go, I will summarize that process. Technique. This is the technique for solving separable equations. And it's simply a summary of the end result of this development. As we go through the course, we're going to see more and more of these developments, and they're going to get longer and longer. And sometimes I'll have to just say, well, you know what, this is so long, we don't have the time or the ability to develop it. You might have some stuff that's just beyond the scope of this course, but we'll still have a technique which summarizes the end result. You are not expected on a homework or on an exam to do the step-by-step process here. You're more expected to use this technique and to resolve using this summary. Right? Starting from scratch is just not really expected. So here's solving separable equations. The technique is if you have y prime, and for now we're dealing with first order problems, nothing else. If y prime equals g of x times h of y, what we want to do is we want to then integrate the integral of 1 over h of y, and my p of y is the same as saying 1 over h of y. 1 over h of y dy is equal to the integral of g of x dx. Once you have that, you'll now have a function of y equals a function of x, and which you would then conclude by isolating y. These techniques will give some conditions. Okay, here's the kind of problem you want to solve, and then it will be a process of, okay, here are the steps you want to take. Those steps right now, you notice it's fairly simple. There's a single major step and then a little algebra cleanup. As we go through the course, these techniques will get a little longer. You'll have 2, 3, 4, 5 steps as required, but they will all basically follow this procedure. Here's the kind of problem you can use this with, and here are the steps that you should take to solve that kind of problem. So let's go ahead and take a look now at some examples of doing this. In fact, let's use one of the examples we saw just a moment ago. I gave an example. I said something like this, dy dx equals 1 plus y over 1 plus x. That is a separable differential equation. That was one of our examples from earlier here. There. All right, well, let's go ahead and see what we can do with this one. Here, we saw a moment ago that this can be separated as 1 over 1 plus x times 1 plus y, like this. Okay, so definitely separable. Okay. So now what we're going to do is we're going to say, all right, now, first of all, let me do the formal way, the official way. What we're going to do is we're going to take this, we're going to reciprocate it, bring it over this way. Okay, so that's going to be 1 over 1 plus y. This one is a function of x. We're going to leave that there. The function of x, we're going to leave that there. All right, so then once we've taken y, and the function of y had reciprocated it over here, and we've left the function of x alone on the other side, we're going to integrate this one with respect to y and this one with respect to x. Okay, so integrate with respect to y and integrate with respect to x. So now we go through and do the integrations. Here, since you're integrating with respect to y, we don't have to worry about substitutions. There's no chain rule or anything. It's just regular integration. It's just y instead of x. Okay, well, the integral of 1 over something is the natural log of that something. Okay, so that's going to be natural log of the absolute value of 1 plus y plus some constant of integration is equal to, and same thing over here, it's going to be the natural log of 1 plus x in absolute value plus a constant of integration. Now, these constants of integration are not necessarily the same. All right, yeah, this one might have a +2 and this one might have a +7, or whatever they might be, whatever's appropriate. Oh yeah, but if I write it like that, they look like they're the same. Oh yeah, I guess they do. So let me distinguish them. I'll call this one C1 and I'll call this one C2. They are both constants of integration. They're just not necessarily the same, so they have a different label. Okay, well, since they're both constants, I do want to isolate my y, if possible. So let me go ahead and take this constant and move it over to this side. Well, wouldn't that just be C2 minus C1? Yeah, it'll be C2 minus C1. Okay. But see, if I write plus C2 minus C1, that's the difference of two constants. Yeah, sure. Well, you know what the difference of two constants is? It's another constant. So here I'm going to write plus C3. By C3, what I mean is, it's just what happens when I put those constants together. I don't actually care what these constants are. So, by putting them together, this is C2 minus C1, and I'm just going to write that as C3. This is a pretty common thing. When you don't actually care what your constants are, you just care that there is a constant. It's common to condense constants together to just give you another constant. Okay. Here, we're now going to exponentiate on both sides. We're going to say e to the, okay, so take e to the this, e to the that, there and there. So here this will give me 1 plus y like this is equal to, and then I've got e to the natural log of 1 plus x, 1 plus x, plus C3 like this. Okay, now you may have noticed, wait, you just dropped that, didn't you? You just did 1 plus y. What happened to your absolute values? Okay, well that canceled out. Well, sure, that canceled out, but what happened to your absolute values? Well, those are going to get absorbed into a constant here in just a moment. So I'm not going to write them just yet here. I'm going to leave these off, and in a moment we'll see where they went. Okay, so here I'm going to work on this side for just a moment. Here, e to the natural log of this plus this. Okay, now remember, there are properties of logarithms and exponentials, and we're going to exploit a few of them right here. Let's think back when math was easy, just regular old algebra. If you have e to the a plus b, that's equal to e to the a times e to the b. Multiplying two things with the same base, you add their powers. Okay, so right here, this is like saying e to the natural log of the absolute value of 1 plus x times e to the C3. E to this times e to the that. Well, you know, this is e to a constant. And you know what happens when you take e and raise it to a constant? You get another constant. So you can call that C4. However, there is a customary notation. You can always call a constant C. C1, C2, C3, C3, C4. You can call it P or W or M. It doesn't really matter what you call your constants. However, there is a convention, and it's one that I tend to use myself. Whenever you have a constant of integration, or actually any constant that's being added or subtracted, we call them C. C1, C2, C3, C4. But whenever there's a constant that's a factor, something that you're multiplying it, you call it M. M for multiply, I guess? I don't know. So here, e to the C3 is M. And since it's the first M that I'm going to see in this problem, I haven't seen any M's before, I'll call it M1. I might end up with an M2 or an M3 later. We'll see. So this is M1. And then here, I've got e to the natural log. Okay, those will cancel out. And this gives me 1 plus x. Okay, those cancel out. Now, one of the things about absolute values is that essentially you're just considering a plus or a minus, right? If this thing in here is positive, well, then you consider the positive value. If it's negative, then you consider its opposite, the negative of a negative, to give you a positive. So you could also write this as plus or minus. So here this is going to be M1, and then instead of having absolute value, I'll say plus or minus 1 plus x. Positive or negative, depending on which one I have. Okay, but now this plus or minus is like saying plus or minus this times this, Well, you know what? I could absorb these together. After all, this is a constant that's being multiplied by a positive one or a negative one. Well, either way, you're going to get a constant. So here what I'm going to do is I'm going to let M2 be plus or minus M1. Right, whether it's positive or negative doesn't matter. It's still just a constant. So I'm going to call this, oh, and you know what? That's bad notation because it looks like it's M1 plus or minus this. It's actually M1 times plus or minus this. There we go. So here, that M2 is going to be the plus or minus M1. Okay, so I'll call that M2 times 1 plus X. But you know, that's what was happening over here to these absolute values also, plus or minus. Oh, well, why don't you just write plus or minus here too? Because this has already got it covered. All right? Plus or minus, it only needs to be written once because everything will either be positive or negative, same sign or opposite sign. So here, I don't write my absolute values because they were going to be absorbed into this plus or minus. That is to say, they're going to be absorbed by this M2. It's not wrong to write them, but it's simpler if we don't. Just keep it all like this together. And finally, we're trying to isolate y. We're trying to find a solution. We're trying to find what y is equal to. Okay, so subtract the 1 over, and you get y equals, let's see, I guess I've got negative 1 now, plus your M2 times 1 plus x. And this is our family of solutions. Note that M2 is a constant. We don't know what it is. It could be positive, negative, and it comes from a bunch of other constants. But you know what? We don't need to keep track of what all those constants are. We don't need to say, oh, by the way, this M2 is equal to e to the C2 minus C1 plus or minus. No, just M2. If you ever needed to find M2, you could find it using some initial conditions. Otherwise, it's just a constant. Note that this is a first-order differential equation, and here you have a one-variable family of solutions. One variable, this being one parameter. This being our one parameter. Later on, when we start having second-degree problems, we'll have an M2 and an M3 somewhere, or a C1 and a C2 somewhere. You'll have two parameters. But for now, first order, one parameter. One parameter family of solutions. That is to say, any number you want to plug in right here will work. If you plug in 17, that will work as a solution. If you plug in 4, if you plug in 9 million, doesn't matter. Anything, any real number right here will work as a solution. Let's take a look at another example then. And in fact, let's go back to something from a previous section. Let's take a look at an autonomous equation. One of the best things about these techniques in differential equations is that for many equations, several techniques will work. One of the worst things in differential equations is that for many of these problems, many of the techniques will work. That is to say, you have options, but sometimes that's not always a good thing because it's hard to tell exactly which one is the one you want to use. Oh, maybe it'd be easier to do it this way. No, maybe it'd be easier to do it this way. Oh, you know what? We actually have to do both to find the full set of solutions, and so forth and so on. So you'll find that just because a equation fits one category doesn't mean it should fit a different one. So here, let's take a look at an autonomous equation. Remember, those are the ones where the variable itself doesn't make an appearance. Here, everything's going to be a function of x, but x will never appear. Okay, so here we're going to say dy dx. So here you have the derivative of y. Technically, there's an x there, right? But that's not really an x. That's just telling you you're taking the derivative with respect to x. You could also just write this as y prime. So y prime equals y squared minus 2y minus 3. Now, y prime and y appear, x does not appear, even though everything is a function of x. Okay? Now you might look at that and say, well, okay, but that's not separable. With separable, you're supposed to have the product of two things, one involving x and one involving y. By definition, an autonomous equation won't have an x there, so it can't possibly be separable. Oh, sure it can. It's got to be creative. Here, I'm going to say y squared minus 2y minus 3 times 1. That's the same as what I started with. But now, technically, That's a function of x. A constant function is a function of any variable, right? It's a function of x, y, z, p, and q. Technically, it's a function of x, and that's good enough for us. So here, the function of x, we're going to divide it this way. Leave that one the way it is. So if you divide I'm going to take the function of y and divide it this way. So this is going to be y squared minus 2y minus 3. You divided by that. Here, the function of x, I'm going to leave it exactly where it was. So that's going to be 1. And on this side, I'm going to integrate with respect to y. On this side, I'm going to integrate with respect to x. So the function of y, divide by it. The function of x, leave it alone. Integrate with respect to y here. Integrate with respect to x here. Incidentally, before I continue here, there is a small abuse of notation that some people will use. This is technically incorrect to do, but it just looks right. So here what I'll say is you can consider it a mnemonic. You can consider it a visual confirmation that what you've done fits. So we know that derivatives are not a fraction, right? dy dx is not a fraction. For example, if I take the derivative of the sine function, I'm going to get the cosine function. Derivative of sine x is cosine x. It's not a fraction, that's just cosine of x. All right, so this is not a fraction. But if you treat it like a fraction, multiply the dx this way, keep it with the x's, divide the y function this way, and keep it with the dy. So it looks like dy divided by y squared minus 2y minus 3. And over here, it looks like dx times 1. That's not actually what you're doing, but it just looks right. It looks like it fits that pattern. And it's a nice mnemonic. It's a nice way of remembering. So that later on during a homework or an exam, you're thinking, wait, which way are these supposed to go? Go ahead and bring all the x's this way and all the y's this way. Like that. dy divided by this, dx times this. All right, so now we can go ahead and integrate on both sides with the appropriate variables. Here, to integrate this, we have a few options, but I think the simplest one is going to be integration by partial fractions. Remember partial fractions? Let's go take a look at that. If I have 1 over y squared minus 2y minus 3, that's the same as saying 1 over y minus 3y plus 1. That factors out that way. But now, by partial fractions, that's going to be a over y minus 3 plus b over y plus 1. And now I can go ahead and use a few different techniques to find what a and b are. Remember that as long as your denominators are distinct, they're different from each other, and they're linear, no irreducible quadratics, no y squared plus 1, everything's linear and distinct, there's always a nice short way to find these constants up here. What we can do is we can say, okay, because y minus 3 is the denominator, then I can never plug in 3, because plugging in 3 would give me 3 minus 3, which is 0. That's undefined. Okay, so cover up the y minus 3. Oh, so since that's not there anymore, now I can plug in 3, right? 3 plus 1 is 4 underneath the 1. 1 over 4. And that's what this is equal to, 1 over 4. Of course, that is a shortcut that only applies if these are linear and distinct. If not, you got to do it the long way. Think back to your Cal 2. Think back to your pre-Cal even, when you first see partial fraction decompositions, and you would do it using the system of equations of a and b. But because these are distinct and linear, we can do it the easy way. Because of this, I cannot plug in a negative 1, because that would make a negative 1 in the denominator. That would make negative 1 plus 1 in the denominator. You can't. That's 0. You can't divide by 0. But if I cover this up, oh, now I can plug in negative 1. Negative 1 minus 3 is negative 4. 1 over negative 4. That's negative 1/4. And that's my numerator there. Right? Whatever I cover, when I cover this one up, and then I plug in the number, that's the number that goes over the one I just covered up. It goes over the y plus 1. Like that. Okay. Of course, these have a common factor of 1/4. So I can write this as 1/4 times 1 over y minus 3. And then plus a negative, I'll just write minus 1 over y plus 1. And there's a nice partial fraction decomposition which I can use over here. So now to integrate, that's the same as saying I'm going to integrate. I factor out my 1/4. 1 over y minus 3 minus 1 over y plus 1 dy equals the integral of 1 dx. Now everything's nicely integrable. Here I've got 1/4. The integral of this one's going to be the natural log of the absolute value y minus 3 minus the natural log of y plus 1, absolute value y plus 1, like that, plus a constant of integration, plus some c, is equal to the integral of 1 dx is just 1x plus a constant of integration. Okay, so now here, let's go ahead and, let's see. Let me go ahead and move this over. So C2 minus C1, that'll just become C3. So that's x plus C3. All right, that one's gone. Now these can be merged together using a property of logarithms. Remember, if you have the natural log of A minus the natural log of B, you can write this as natural log of A over B. So here I'm going to have 1/4 natural log of absolute value y minus 3 over y plus 1. Like that. That's already gone. These two have merged together. I'm trying to isolate my y. So what I can do here is I can multiply both sides by 4. So this will be natural log absolute value y minus 3 over y plus 1 is equal to, let's see here. I've got 4 times x would be 4x. 4 times C3 would be 4C3. But 4C3 is just another constant, so I'll call that C4. And see how that works? I don't really care what that constant is, just the fact that it's a constant. So multiplying it by 4 turns it into a different constant, but it's still just a constant, so plus C4. Okay, so now I need to exponentiate on both sides with a base of e. So here that's going to be y minus 3 over y plus 1 equals, and the same trick that I pulled before in the last problem, because here this is going to be e to the 4x plus c4. That's really e to the 4x times e to the c4. And because that's multiplied by e to the c4, that's a constant, I'll just call that m1. That's m1 e to the 4x. And that's where the e to the c4 became my m1 that's being multiplied in. Of course, here, the absolute value, that's really a plus or minus, yeah? You can think of that as plus or minus the values in here, and that gets absorbed in here. So whenever we exponentiate, the absolute values are going to go away because they're going to be absorbed into the constant. So here, I'm going to write it as plus or minus right here. But note that as we go forward, you're going to usually see me just jump directly from, I'm going to exponentiate and I'm going to get rid of my absolute values, because that's the trick we're going to pull every time. We're going to take the plus or minus and absorb it into the constant. So this becomes y minus 3 over y plus 1 equals, that's just an m2 now. The plus or minus joins the m1, like this. And now we're back in algebra. We can solve for y here. We multiply both sides by y plus 1. Okay, so this is going to give me y minus 3 equals this stuff times y plus this stuff times 1. Okay. Anything that has a y in it, let's join it together. Anything that doesn't, let's move it the other way. So here this is going to be y minus ym2e to the 4x. And over here, I'll add the 3 over this way, giving me 3 plus m2e to the 4x. Your y terms come this way. Anything that doesn't have a y goes this way. Y is now a common factor, which I can factor out. Y times 1 minus m2e to the 4x is equal to 3 plus m2e to the 4x. And finally, divide both sides, and we're done. We have that y, the solution to our autonomous equation, is equal to 3 plus m1e to the 4x over 1 minus m1e to the 4x. And this is our solution. One thing to note here, recall from our previous sections, so note, since y squared minus 2y minus 3, y squared minus 2y minus 3, the right-hand side of our original problem, equals to 0. Since that equals to 0 has two solutions, let's see. If I factor this thing, that's going to be y minus 3, y plus 1 equals to 0. So it would have solutions positive 3 and negative 1. So here I have a, oh, sorry, this should be M2s. Whatever, just trying to be consistent. Here we have a one parameter family of solutions. You say, well, there's two parameters right there. No, it's one parameter. It happens to appear multiple times, but there's still just one parameter. This is M2 for both of them. Okay, so there is only one parameter, even though it appears multiple times. Okay, so our first ordered ODE has a one parameter family of solutions. Yeah, okay, we were expecting that. But we know these are solutions too from what we saw in a previous part of the chapter. We know that these are solutions to an autonomous equation. Whatever the zeros of this are also serve as solutions. Notice that will never happen here. Notice that for any value of, let's see here. Oh, you know what? Let me just do it algebraically. I was going to make a general statement, but I can actually just plug things in. So here, let's say I was trying to get y equals to 3 out of this. After all, this is a family of solutions, and these are solutions. Shouldn't they be in here? Well, let's see. Y equals 3, y equals that. Well, then surely there's some value of m2 that makes this whole thing equal to 3. Well, let's see if we can do that. So 3 equals 3 plus m2e to the 4x over 1 minus m2e to the 4x. Let's see if we can't pull that off. Okay, so let me multiply this to the other side. That's going to give me 3 times 1 is 3, minus 3 times m2, 3m2e to the 4x, is equal to, I've brought that up this way, but the 3 plus m2e to the 4x, that's going to stay like that. There's a common value of 3 on either side, which let me subtract that from both sides, minus 3 from both sides. And this will give me negative 3 m2e to the 4x equals m2e to the 4x. Okay. Finally, we can go ahead and subtract this over this way, or sorry, add this over this way, and this gives me 0 equals 2. I've got 1 m2e to the 4x, and I'm adding another 3 m2e to the 4x. It gives me 4 m2e to the 4x, just like that. But note that your e to the 4x is always positive. Remember what the graph of e to the 4x looks like. It looks like this. It never reaches 0. It's always positive. 4, of course, is just a constant positive number. What about m2? Well, if we go back to how we found m2, m2 was, oh, let's see, where was m2? Here we go. m2 was plus or minus m1. Okay, what was m1? Well, m1 was e to the c4. Well, again, e to the c4 is always positive. It's never 0. Oh, well, here it's plus or minus. Okay, positive or negative, still never 0. If this is not 0, changing its sign won't make it 0. So here, this number is never 0. This number is never 0. And 4 can't be 0. So the product of three things that are not 0 cannot be 0. Which, since m2, 4, and e to the 4x are all positive, this is impossible. Okay, so what does that mean? That means here's our family of solutions. This is a solution, but it's not a member of this family. We've mentioned this before. When you have a family of solutions, that doesn't mean it's all inclusive. It means every member of this family is a solution, but there might be other solutions somewhere else that are not a part of this family. So here we have, by the way, the same thing is true for y equals -1. You can do the same thing and you'll find y equals -1 doesn't work either. Same for y equals -1. So the equation y prime equals y squared minus 2y, what was it, 2y minus 3, has solutions y equals 3 plus m 2e to the 4x over 1 minus m 2e to the 4x, but also has solutions y equals to 3 and y equals to -1. Remember that when you have solutions that are outside of a family, they are solutions, but they're not a member of the main family of solutions. These are called singular solutions. A little review of vocabulary from previous sections. Finally, we have one more example here where, well, recall. This is a consequence of Cal 1. If f is a function that is continuous, on some interval that's given by x naught up to x, where x naught is fixed, it's the beginning of an interval, and x is variable, it goes up to as far as you need it to, then the function capital F of x, given by the integral from x naught up to x of the little f of t dt, is an antiderivative for f on the interval I. It is an antiderivative of that little f on your interval I, on I, where, and here's the part that's important for our purposes, where f prime of x, since it is an antiderivative, it is differentiable and therefore can fit the terms of our differential equations. Here f prime of x being the derivative with respect to x of the integral from x naught to x of f of t dt. This is just our regular old f of x, the fundamental theorem of calculus. The derivative of an antiderivative of a function is just that function with that variable in place, like that. Okay, sure, that's the fundamental theorem, but what does that have to do with solving a differential equation? Well, sometimes these integrals are not ones that we can directly do. Here, I had to integrate this, and I used partial fractions. And here, I used the product rule. And over here, I used the logarithm rules for the previous example. And there's a lot of rules that we know how to, from Cal 2, that we can use to solve to find integrals, to find antiderivatives. We can use the product, the integration by parts technique. We can use trig substitutions. We can use U substitutions. We can use any number of different techniques. But we've seen that even those techniques are not always sufficient. There are some integrals that you just cannot find an elementary solution for. At the very least, you may need to drag out the Taylor series to do that. There is, in later parts of the course, a chapter where we're going to have to do that. We're going to have to drag out some Taylor series to get certain things done. But for now, we can use this. We can use the results of the fundamental theorem of calculus, the consequences of the fundamental theorem, to state our answers using an integral form rather than using an explicit form. What I mean by that is, for example, consider the following initial value problem. It is y prime equals cosine of x squared over y squared. Okay, so definitely separable. But since it's an initial value problem, it should have an initial condition. Here, y at 1 is equal to the cube root of pi, because isn't that a fun-looking number? Over the interval where I goes from 1 to infinity. And over the interval from some fixed constant number to some arbitrary number on the end here, where it's just going to go off to infinity. Okay, well, this is separable. I can take the y squared and bring it over this way. That becomes just y squared, not divided by anymore. Over here, cosine of x squared is just going to stay right where it was. The function of y, I integrate with respect to y. The function of x, I integrate with respect to x. Standard technique for a separable function. However, at this junction, I realize that is not an elementary solution. Cosine of x is nice. Cosine squared of x, I'd have to use a trig identity for. But cosine of x squared, you may or may not remember from Cal 2, this is an example of a non-elementary integral. That is to say, there is no combination of polynomials, rationals, radicals, trig functions, hyperbolic functions, or any other nice known functions that are the antiderivative of this thing. In Cal 2, you would have pulled out a Taylor series. You would have taken the Taylor series of cosine of x, used substitution to find the Taylor series for cosine of x squared, and then integrated that term by term and tested for its convergence. Are we going to have to do that here? We could, but no, we're not going to. Because on the interval from x naught to x, an antiderivative of this function here is the integral from x naught to x of that function. Same thing here, where that function is with respect to t. So here, instead of taking these antiderivatives, I could take this one, but I'm going to go ahead and do the same thing for both, since I would have to do it for this one. I'm going to go ahead and write this as the integral from 1 to x, from 1 to some arbitrary x value of, now take your functions in terms of t, so this would be t squared, from 1 to, t squared. Same thing for this one, it's going to be the integral from 1 to x of cosine of t squared. Now let's see here, that's going to be, dt, like this. Oh, actually, my apologies, that's not quite right, is it? This is fine, but over here I said this is going to be t squared. No. Here my substitution is for x, not for y. So here it's not y squared becomes t squared, it's y of x squared becomes y of t squared. My apologies. So y, it's still y squared, but now it's y of t instead of y of x. And then here my dy is going to be y prime of t dt. There we go. X is becoming t, not y. There we go. Okay, so now I can integrate this thing, and that's going to be y cubed over 3, which I could have done, I could have done that earlier, but whatever. I'm going to go ahead and do both sides the same way. Y to the third over 3 of t, evaluated from t equals 1 to t equals x. Over here, you say, well, all right, fine, you were able to do this one, but you could already do that one. Here, you won't be able to do this one because you couldn't do that one. Okay, well then don't do it. Leave it that way. Here, we're going to leave it in the integral form. You might wonder, can I do that? Sure, why not? We leave things in incomplete forms all the time. When I write the square root of 17, no one is really terribly bothered by the fact that I didn't grab a calculator and say, oh, that's 16, that's 4 point whatever. No, it's just the square root of 17. We leave things like that all the time. All right, so what's wrong with this? We're going to leave it this way. So let's see here. That's going to give me y cubed of x over 3 minus y cubed of 1 over 3 is equal to, and of course there's nothing really I can do here, so let me just leave that the way it is. Integral from 1 to x cosine t squared dt. Okay. I'm trying to isolate my y as my solution, so let me go ahead and multiply both sides by 3. So this gives me y cubed of x minus y cubed of 1 equals 3 times integral from 1 to x cosine t squared dt. Here, notice that y at 1 is a known value. It's the cube root of pi. Oh, but it's being cubed. Okay, so it's the cube of the cube root. This is y cubed of x minus, again, y at 1 is equal to the cube root of pi, but then that's being cubed, so that's just going to give me pi. And since pi is a constant, I can add it to the other side and isolate my y cubed. So here I get y cubed of x equals 3 integral from 1 to x cosine t squared dt plus pi, like that. And finally, I'm looking for y, not y cubed, so I can take the cube root of both sides, and I get y of x equals, so the solution to my initial value problem is going to be y of x is equal to the cube root, to get rid of the cube. It looks weird to me to write the pi on the end, so I'm going to write it at the beginning. Pi plus triple the integral from 1 to x of the cosine of t squared dt. And there we go. If we ever really needed to, notice this is a function of x because x is that value up there. If we ever really needed to, we could go through and evaluate the integral using a power series. You know, we could do it numerically by knowing what number that is and using something like Simpson's rule or the trapezoid rule or whatever. But here is the answer. If we ever needed something evaluated, we could do that, but otherwise we're going to leave it this way. I have mentioned before that one big difference between mathematicians and the rest of STEM is that mathematicians are concerned with the general solutions, and we don't really care about individual particular solutions for many types of problems. Another major difference, however, is that mathematicians are perfectly comfortable leaving things in a symbolic form, whereas everyone else wants, well, yeah, but I want a decimal, or I want a fraction, I want some closed form thing. Mathematicians are comfortable leaving things this way, and so we'll leave it this way. So that's the end of this topic and the end of this section. If you have any questions, please feel free to let me know. Otherwise, I hope everyone has a nice day, and I will see you all next time.